you should be able to see my screen. And these are the notes from the discussions we've had so far. So people have mentioned memory, and mostly you see me draw this box on there, mostly referring to the RAM itself, not necessarily the secondary memory, right? I hope you can all hear me loud and clear. Somebody just say yes, and I'll be a happy person. Good. So you've got your RAM sitting on there, and from what you have said, you've actually separated primary memory from secondary memory, and you gave a couple of examples, things like cache, the RAM, or basically, let's go for RAM. I'd rather use that, right? Which is random access memory, okay? And this would be a capsem, and of course I had to type this really fast. Then you've got your secondary memory, which is things like hard disks. You can have your hard disks and other things sitting in there, or USB flash drive and all those kind of things. And then somebody mentioned also that, of course, your CPU most of the time interacts with memory. So CPU gets its code from your RAM, and of course your operating system and other things mostly sitting here because it's non-volatile. Non-volatile simply means that once you switch off your computer and switch it back on, you still have your information stored for you. Okay, volatile means that once you switch off your computer, you've lost the data, right? So if things like OS you need for the computer to run sitting there, or the files and other things you save for yourself, great. But things are going to be loaded onto your RAM for you, and you've heard of things like basic input and output system. So you've heard of BIOS, which is basically helping the whole processor boot up, and then when you switch it off and all that. But anyway, if you've got things being loaded into RAM for you, which is basically ones and zeros, right? And you can tell as we dig into the architecture, we'll just be looking at low level, high level, and all those kind of things from that aspect. So it gets loaded into memory, CPU interacts with it. Yeah, then you mentioned that secondary memory. Someone did say that it's not directly accessible by the CPU because the CPU doesn't interact with it directly most of the time. But you can say there is also something called DMA, direct memory access, that kind of sometimes allows CPU to skip certain things, right? And of course, yes, it is slower than secondary memory. So let's draw something. This you'll probably come across this a lot, but I'll do that, and because my drawing is horrible, I'll just really, it's meant to be a triangle, okay? Just take it as a triangle. So you just have your secondary memory sitting at the bottom, and then your primary memory sitting at the top. And what that means is that if you picture your CPU here, it means the closer you are to your CPU, the faster you are, right? And earlier we say that the cache may be sitting on the same architecture as the CPU, or the same hardware device as the CPU, right? So you can have cache sitting there. But part of the CPU, another person also mentioned registers being part of the CPU. The cache, we can actually split it into level 1 cache, and then we can also have a level 2 cache as well. Just level, okay? Level 2 cache. Then you can even have a level 3 cache sitting on there as well. And sometimes, depending on how level 1 and level 2 cache are, you can also have them also on the same device. So it's just the same cache that I've split down, okay? Then, of course, you come to your RAM. So moving at this point, we're moving sort of from the CPU onto another different chip or another, so further away, right? Then you go to your RAM, right? Then you have your secondary memory sitting somewhere there. So let's say SM. Hopefully my handwriting is not that horrible, but you can catch it. But then something else sits at the bottom, which is virtual memory. From your own presentations, people say, yes, virtual memory is not real. That's why it's called virtual. It's not your physical device, right? It's just basically borrowing some of the memory from maybe an actual physical device. Maybe if your hard drive is 3 terabyte, for example, and you are playing a game that requires maybe 4 terabyte. Yeah, so 3 terabytes is all we have in terms of extra current available hard drive space, right? And then the extra 1 terabyte will just be borrowed. So basically we have this 3 terabyte, let's put a 3 terabyte in RAM, for example. Let's make that easy. 3 terabyte from RAM, and then the hard drive, of course, processor interacting with memory, the hard drive need additional 1 terabyte. It can borrow that additional 1 terabyte from the hard drive, so the in RAM, it appears as if we've got what? 4 terabyte. So it appears as if we've got 4 terabyte worth of space available. But because, of course, it still needs to be a physical hard drive space. But currently, our memory space appears as if we have 4 terabyte. No, I'm just using huge numbers. It appears as if we have 4 terabyte space available. But this is an actual physical hardware space. 3 terabyte has an address, maybe, I don't know, address 2K to 2K plus 3 TB. Address 2K to 2K plus 3 TB. Let's take that. Handwriting going horrible again. But this 2K plus 3 TB on the memory, we have only 2K plus 2 TB. The additional 1 TB is coming from hard drive. We have to give a virtual addressing system that make this appear as if it is a contiguous region or it can be accessed fully. But this virtual addressing also need to be translated to a physical space. So it takes several steps to interpret all these addressing system in order to get the actual data. That is why virtual memory is a lot slower than both the actual physical ones, because there's a lot of interpretation going on. Then that takes us to the cache. So earlier we said the cache can be, people, they say, yes, the cache, when the CPUs needs information that's recently used. So you've got your memory, it takes the information, it puts it into cache. So if you've got a case where, let's say, you keep doing something like, you have a for loop that simply say you're just going to do x equals x plus 1. And you're going to run this 100 times. Yeah, you're going to run this 100 times. It means that you will need x again. So it's better to store the recently used x in a memory that is closer to your CPU. Yeah? So basically, if x is there, then of course recent iteration, if x is 9, it will just take 9 and then you add 1 to it. It doesn't have to go all the way back to main memory. So it sort of speeds up the process really well, right? At the moment, I'll just take here. Maybe I may or may not go. Let's go into level 1, level 2 cache and other things. But then remember, you need 2 set of information in order to find the physical place and get information from there. You need your what? You need your address, and then you need the actual data that is stored there. So this can be a level 1 cache that is part of the processor itself. And normally this comes to play when we have several processors on the same chip. So each processor, of course, have its information it's working with. And of course, this comes into multi-core systems. So you have multiple processors. So you have CPU 1, CPU 2, or CPU 2, CPU 1, whichever one. So it will also have its own level 1 cache, where maybe the cache is the address and data are split. So it's not unified. So we can have another level 2 cache. Level 2 cache can be quite similar, but mostly it will probably be unified, where you have the address and data unified. The advantage, of course, of splitting the address and the data is easy to get information. It's a lot quicker. So you have level 1 cache mostly, of course, be much closer to your processor, being a lot faster. Then you can have your level 2 either sitting on the processor or probably slightly away from it. But most of the time, your level 2 cache will be on the processor as well, or the same technology. Are we okay up to this point? Can I have a yes? If no, I can't see the chat, so simply scream at me and I'll see. Good. I see chat, so that means say yes. So we continue from there. But because we are using multiple processors, and we can have another level of cache, which is level 3 cache, before we even go into our memory. And then, of course, you have things like memory controller, which controls access to the memory, right? So the level 3 cache will be visible to maybe a bunch of CPUs. Maybe you have, if we are using clusters, for example, right? So we can have a cluster of, let me just use some small dot to represent a CPU. So you can have another cluster of CPUs which share a level 3 cache, for example. So these CPUs are, of course, I should draw it from the level 3, level 2, are, of course, sharing a common cache just because they may be working on the same code with data that needs to be shared among these caches. Please, if you need a question, if you have a question, just simply turn on your microphone and ask, because I can't see the chat at the moment. So then it'll go to level 3 cache before, but it's not always that we will have it in this architecture. But multi-core help us understand what is happening. So yes, somebody did say something. So if, let's say, X has been replaced and we don't find the data in there, then it's called a cache miss. If X is available and we find the data in there, it's called a cache hit. Now, think about it. You've got multiple people with the same bank account, right? Multiple people who want access to the same money, which is the same storage device. Sometimes there will be conflicts. Sometimes there will be, maybe someone has gone for, if there's a check, another person has already cashed it out, and then you are still going to try and cash it out. They may be working with data that is outdated and all those things. So hence there are things like cache coherency protocols, which basically is a set of protocols or various algorithms that people have come up with that you can follow to ensure that you these processes work with the right data when they have to. So that sort of touches on cache coherency protocols, just a touch on that. So people talked basically about the computer architecture, basically what makes what works, and how the various components of the computer and system and how they are interrelated with each other, right? Then you have things like you talk about people who do the actual design for you and other things like that. Okay. Then people mentioned the CPU or the processor is the brain of the computer. If you have a question, please ask. So you have your CPU being one device, and you can have a core being part of, you can have a core, which is still a processor. Let's represent a core by a circle, which is still a processor, but you can have several cores that are maybe processors, GPUs, or other things in a multi-core system or on a multi-core chip, right? Of course, it's not arranged in this order, but you get the point. Right, and within the CPU, you've got, I put a question mark here because it's not always the case. It's also, it can say it tries its best, but it depends on the bus and the instruction that is being executed and other things. Then you mention things that like the arithmetic and logic unit doing the mass crunching for you. So you have your ALU doing the math stuff for you. And then someone mentioned an instruction register. Which a register is just basically, think of it as a tiny little memory on the computer. It's a storage space, but the processor uses it to monitor itself and other things, okay? Or to run its operation. So you've got the registers and closest memory to the CPU. Also the instruction register in there, it can help you decode what the instruction is or the actual instruction is. Then in here, we're doing all the maths calculations and all those kind of things. You can have a controller to, of course, control everything happening in the CPU for you, right? And you can have interaction with your memory because that's where your code is sitting. And if you are taking, of course, a Harvard architecture, we can split the address and then we can split the data bus. So you have two things. If you are going on address, you can actually say, because it takes you to the memory, you have memory address bus, or you can have a memory address register, for example. It's just an address that it's just register that help you interpret where the address location is. And then you can have a memory data register, which help you access the data in memory. Then it can come back to the system, for example, for like this. Okay, so then we have processor definitely interacts with memory. Memory is a storage device where data is stored in. This point should go into the previous slide. cache is like RAM and other things coming from other people. It is temporary, and someone made a good point that, of course, if you keep trying to find information, if you keep trying to find money in your pocket because your pocket is the cache and it's not there, you might actually be wasting your time and other things, right? So we drew the memory hierarchy where we said register is closest, virtual memory sitting at the bottom. What you need to know is that the closer you are to the processor, the more expensive you are. Because, of course, CPU technology is quite expensive. And we said we can have similar technology for even for caches and other things. So the closer you are to the processor, the more expensive you are, but the faster you are, right? So this means the more you move down, the slower the memory system is. But because these are fast, but they are fast, but they're expensive, we can't really have large sizes of them. That's why you have hard drive being in order of terabytes or more, and then probably as you get closer to cache, you just more resort to things like megabytes and other things, right? Previous years probably would have been kilobytes and all those things. Okay, so we have talked at length about virtual memory, and yes, this was right on the point that, of course, CPU borrows memory from it. And it's not physical in the sense that the address location you are looking at is not necessarily a physical location. Right, then people talked about Harvard architecture. When we started, we had a von Neumann architecture. Von Neumann was among the first, actually revolutionized the computer architecture to separate the CPU or the processing. Let me use processing, separate processing from memory. So separate the code and the processing. So in that case, it gave us the ability, of course, to load different code to do our programming for us, right? So we separated them. But we had one bus, and whoever talked about bus too, thank you so much. Bus basically helping us to transmit information. We've got the same link for address and, of course, for data. So what that means is that information is placed on this particular line. It wait for it, go to the data, come back and bring it back. It was so slow. So when you say von Neumann, you hear things like von Neumann bottleneck, right? Okay, so then Harvard sounds fancy. Sounds modern. Say let's separate the address and the data bus, right? So if we have separate address and then data bus, then we can go through one link for the address to get to the particular address, get that information, place it on the data bus, and bring it back into the processor. And of course, serial and then parallel communication, just basically data transmission. You can just transmit several bits of data at the same time, and then serialization is one bit at a time. I will stop this slide recording at this particular point in time.